This project is truly revolutionary. It's never done, specifically not in this size and this scale.
For us, it's more than commercial. We believe in decarbonisation of this planet.
Innovation doesn't exist without taking risk, but we think that this technology is really a game changer. The maritime industry is an extremely hard industry to decarbonize, so there's not many tools that you have. So it's really important that we as users of the maritime industry are also going to get involved in some of the innovation and really move the industry forward.
Cargill phoned us and said, could you actually invent a wind propulsion system for us? A system that we could put on our vessels and decarbonise the deliveries of food around the globe. They arguably know more about shipping than Bartek. We're the techie guys knowing how to invent things, and that partnership's been really, really strong. So we fed off each other, and that's about energy, expertise, technical know-how, and drive and determination, because what we've done together is not easy. Otherwise, everybody would be inventing wind for ships.
We were looking for interesting technologies that we could bring in-house in order to make the maritime industry greener. And then we came across Bar Technologies with the assisted wind propulsion as a super cool technology to embark in. If you look at the Pareto of the savings, meaning how much you can save per technology, wind propulsion is one of the biggest levers you have.
There are so many energy-saving devices in the market today. Wind-assisted propulsion system is one of the very few solutions available that can achieve fuel savings by 2 digits, and it can be retrofitted.
One of the strong learning points in the shipping industry is it's all about partnership. Without a very strong collaboration of Cargill, MC Shipping, COSCO Shipyard, Bar Technologies and Yara Marine Technologies, we would not have been able to bring wings to the water that fast.
The wind wing's made up of 3 elements. Each of them are 37.5 metres tall. The middle one is 10 metres wide, and then the front element is 5 metres wide, and that's a duplicate of the rear element, which is also 5 metres wide. And they work together, so each of those elements has a central pivot, and the whole wing also rotates, such that we can actually present that wing in many different angles, in many different formats, depending on the wind angle and the wind speed.
This innovation is extremely important for the maritime industry because it is a technology that is actually using wind, which is a free fuel in the end of the day.
Each of these wind wings is saving 1.5 tonnes of fuel a day. That's 4.65 lower CO2 emissions per wing per day. That's next level savings.
We hope to gain a lot of insights from Pyxis Ocean, which would open the doors to expanded application to other ships in our existing fleet.
The real fight is the legacy fleet and these new builds in the future, to bring the grain in the case of Cargill or other goods around the world and emitting far less.
Where we're going to spend our time on is how can we scale this technology not just on our own fleet within Cargill, but also very much in the rest of the industry.
Just like an airplane uses air pressure to move upwards, the Oceanbird wing sail uses it to move forward. The air under the wing is slowed and deflected downwards, which generates a pressure on the wing. The airflow on the other side of the wing goes faster than the air beneath, and the pressure differential generates lift. The wing is also resisting the airflow, generating another force called drag that pushes back. To generate the most thrust forward, it is important to position the wing to get the optimal angle of attack from the wind. Therefore, the wing sail follows the wind, and unlike a plane, the wing must be symmetrical to be able to take power from the wind on both sides. However, the symmetric design has no curved camber like a textile sail when the wind blows, which optimizes the power that you can harvest from the wind. That is why the Oceanbird wing sail consists of a mainsail and a flap. They form an asymmetric shape where the wind is accelerating on the outer part of the wing and is decreasing on the inner part of the wing. This increases the lift and therefore the overall performance. By this design, we can adjust the overall shape by changing the angle of attack and create camber, which dramatically increases the performance. Now, let's take it a step further and look at how wind and wings interact under navigation conditions. The actual wind is called true wind. When sailing, The vessel itself is also generating its own wind equal to the speed of the vessel. Apparent wind is a combination of true wind and speed wind due to the vessel moving forward. In reality, the apparent wind will often have a direction close to the bow, which is a general challenge in sailing. However, the wing sail shows good performance for these conditions. It will automatically adjust its position, providing the best thrust forward to the vessel by setting the optimal combination of lift and drag. When the wind is growing too strong or when entering harbors or passing under bridges, the flap folds to the mainsail before the whole wing is tilted.